Hi, welcome to XMaths. My name's Lee and it's good to be back with you. Today we are going to do our second session on calculus. Now, if you remember the last time we got together and we looked at calculus, we dealt with all the basics behind actually working with it. Now we're going to actually see some applications of how we go about working with calculus. And this is where the real beauty of calculus starts to shine. We're still going to do one more session on calculus, so today we won't get through all the applications, but we'll at least touch on some of them. So let's have a look at what we've got planned. Right, let's have a look at our outline of what we have planned for the next two sessions. If you look over here, I've called it calculus applications because this is really where we start working with it. The key concepts we intend to cover is firstly the concept of a tangent to a curve, then how to sketch a cubic function. A cubic function is a power 3 equation. Graph interpretation, which you will know about from all your other graphs. We're just going to now carry it into the cubic function. And then maximum and minimum problems, which I'm sure we won't get to this time, and rates of change or calculus of motion, which I'm sure we won't get to as well. But we will slowly address those as we go. So let us start by first looking at the first concept, which is the equation of a tangent to a curve. So let's have a look at this and let's talk back to when we actually had the graphs and we were talking about what it meant to be a tangent to a curve. So let's suppose we've got a parabola of some sort here. And as we had discussed last time, we talked about how a tangent to a curve would look like this. And if you remember, I'd stressed that at this point, the gradient of this curve is equal to the gradient of the tangent. Now, of course, the gradient of this curve keeps on changing. But at this point, whatever that gradient is, will be true for that entire line. So it's quite an important thing to be able to do. And we're going to be working firstly with how to get the equation, knowing the point of contact. And then later on, I will give you this equation and ask you to work back to find the point of contact. So starting with the first option, if we're trying to find the equation of a straight line, we need to know at least one of two things. We need to know two coordinates, or we need to know one coordinate and a gradient. Now, looking at this, if I've given you this point of contact, we know one point. What we need to do then is just find the gradient. So first thing we would do is we would see if we have the point of contact. Point of contact. Okay, if we have it, then we have no problem. We might only have the x value. So if we have only the x value, we would substitute back into the equation of the parabola to find the y. Right, so then we'd have the point of contact. Then we would know that the gradient of the curve must equal the gradient of the tangent. And of course, we know that that means the derivative of the curve must equal the derivative of the tangent. Right, so let's have a look at an example, and I think it'll start to make sense. It says, calculate the equation of the tangent to the curve f of x equals 3x squared at x equals 2. So we know the x value, we don't know the y value. How would this curve look? We don't have to be able to draw it, by the way, but it's always fun to get a picture of what we're looking at. So we're looking at a positive parabola, it's smiling, and we know it's going to have its turning point at the origin. And now I'm saying to you, at x equals 2, somewhere along here, I want to find the equation of the tangent there. Now, to find the y value will not be problematic, because all I would do now is I would say to myself, well, look, I know x is 2, and I know the equation of the parabola. And that point is the point that is common to both of them, so all I have to do is substitute in that x value, and I can calculate my y. So let's have a look. I would say, what is the f of 2, which is 3 times 2 squared, which is 3 times 4, and 3 times 4 is 12. So this is the coordinate 2, 12. Now, knowing that, I need to find this one's equation. Now, as I said to you, to find the gradient, we need to find the gradient of the curve and put it equal to the gradient of the tangent. So the gradient of the tangent equals f dashed at 2. So let's start first of all with f dashed of x. Now we know we did last time some shortcuts on how to do this. So what we would do is we'd look at this and we'd say, okay, if I look at this, I can find the derivative very easily. It's going to equal 2 times that is 6x. Now f dashed of 2 then is going to be 6 times 2, which is 12. So therefore, the gradient of the tangent is equal to 12. Plus we have the point 2, 12. I must say I didn't write that too nicely, so let's just write it nicely. Now, of course, this is a straight line, and if it's a straight line, we have the option of using y minus y1 equals gradient x minus x1, or if you wish, we can use y equals mx plus c. This is really very much a choice. Some people just prefer the one form to the other. I prefer the one I wrote at the bottom. For me, it is the more effective one, simple to use, and you get your equation straight off, no problems. But if you use the top one, it's really no difference. So I'll do both, and you can decide for yourself what makes you more comfortable. So if we go to the one I really like, this would be my x1, and this would be my y1, and this would be my gradient. So I'd go y minus 12 equals 12 times, and here I would have x minus 2. So what do I have? I'd have y minus 12 equals 12x minus 24, which means y is equal to 12x. And if I say 24 plus minus 24 plus 12, I'm going to get minus 12. So that is my equation of the tangent. Let's see if it makes any difference if I go this route. So I know that the gradient was 12. And I'm now going to substitute this point in. So I'm going to say 12 equals 12 times 2 plus c. So 12 is equal to 24 plus c. So c is equal to 12 minus 24. 12 minus 24 is minus 12. And so we have the equation y equals 12x minus 12. As you can see, there is no difference between those two equations. So it's really very much a choice. It's up to you. I'm sure that if you've been watching my other sessions, you know that I have been stressing the bottom one as the easier one to work with, less dangers and more chance of being in a better position to get the equation right. All right, let's see another kind of question. Another kind of question says, determine the value of k for which the equation of the tangent to this curve at this point is that. Now notice they're not giving you the full point of contact, but they are telling you the x value. Now, can we go and substitute and get the y? The answer is not at this moment in time, because if we look over here, this equation's not complete. If that equation's not complete, we can't find our y. So we're not going to be able to work that out yet. So let's see what we can do. They've told me the equation of the tangent is this. In other words, they've told me that my gradient is 8. In other words, the derivative of f at 2 is 8. Or in simple notation, f dashed of 2 equals 8. So what we have to do now is we have to find f dashed. So let's start first of all with what we knew. We knew that fx is equal to 3x squared plus kx plus 4. So f dashed of x will be 3 times 2 is 6x plus k. Now f dashed of 2 is going to be 6 times 2 plus k, so it's 12 plus k. But they have told me that this 12 plus k must in fact equal 8. And so k is equal to 8 minus 12. In other words, k is equal to minus 4. Okay, so that was easy enough to do. We found the k. And do you agree with me at this stage, if we wanted to find y, we would be in a position to do that because we know what k is. So we've got the equation now. But they didn't ask me for that, so let's not go there. So notice there were two approaches. The first one was when I was given the point of contact or part of the point of contact and asked for the equation. And the second one is where I know the gradient of the tangent, and I have to find the point of contact or some other bit that's missing in an equation. Relatively straightforward, nice application, asked very often in the middle of graph interpretation, and I'm sure we will hit one or two of those when we actually do our graph interpretation. Right, so for now we need to stop a little bit and look at some algebra, which happens basically in your paper 1, but it's only designed wholly and solely to serve our calculus. We need to know about remainder and factor theorem in order to be able to work with our cubic equations. So I'm going to stop for a bit and sort of do a little detour. This is a separate section if you like, but it's so intricate to how we do our calculus that I've made it part of this session. So let's have a look. It's called remainder and factor theorem. Now what it says if a polynomial. Now I can already hear you groaning. Why do we have to use these dreadful words? Well, it's not that dreadful. A polynomial is an expression, and I'm sure you remember from when you were young. It's an expression with adding and subtracting signs between it. What is important is we never have a negative exponent, and we never have, well, the negative exponent would imply we don't have a dividing by a variable, and we don't have any surds in it. That would make it a polynomial. So it's just some expression. It could be x cubed plus 3x plus 2, or it could be x to the 5 minus 7x plus 7, for example. Those are all examples of polynomials. Anyhow, it's not too much to get worried about. It just means an expression without dividing by a variable or without a surd. So if a polynomial f of x is divided by ax minus b, then the functional value of b over a is equal to the remainder. Now this is what we call the remainder theorem. All right, we also have the factor theorem. Now I'm going to spend some time talking about these in a moment. They're not too important, as I say. You just need to be able to use them effectively. But I will do the bare essentials with it. Basically, it says the same thing. It says if a polynomial f of x is divided by ax minus b, then if f of b over a equals 0, ax minus b is a factor of f of x. Now, what I mean when I say something's a factor, let's take the number 6. If we're dividing 6 by 5, we would go in once, remainder 1. But if I take 3 and divide it into 6, it'll go twice and there'll be no remainder. And then I would be able to say that 3 is a factor of 6, because when I do the division, there is no remainder. So this makes perfect sense then. So I'm saying to you the remainder is 0. And because we understand that if the remainder is 0, it's a factor, that's the problem solved. Now you might say, oh my goodness, this is so complicated, so difficult. Don't worry. It's really not a problem. I need to spend a little bit of time just building a case for you here, and then we'll move on, because we're not going to kill this section. It's not that important that we need to do that. All right, so let's go down here, and let's take something like x squared plus x, say plus 12. And I say to you, that is my f of x. Do you agree with me that that would be a polynomial? Well, yes, there are many terms. They're separated by plus signs. And yes, there's no denominators with x's, and there are no surds. So it's all good. Now, if I say to you, divide f of x by x plus 2. Now, I'm sure you would have seen this somewhere along the line. It's really quite a painful experience, and I'm going to do it the long way just once, because I think it's important you see it once. And then I'm going to show you how this theorem would make your life so much easier. And I'm going to show you another way of doing this long division that you don't suffer. The first thing we're doing is we are going to use the good old-fashioned algorithm, where I'm sure you've seen it before. Daddy, mommy, sister, brother. And that stands for divide, multiply, subtract, and bring down. So what we're doing is we're taking it like this and we're saying let's put our x squared plus x plus 12 there. And let's put the x plus 2 there because we want to divide that into that. Think back to when we used to work with numbers. So say we had 201 divided by 5. You agree with me? We go 5 into 2 doesn't go. 5 into 20 goes 4 times. So that would be the divide step. So the equivalent in the algebra would be to say x divides into x squared x times. Then what did we do? We said, right, 4 times 5 is 20. In fact, let's make the number a bit bigger. So we said 20. Then we would say, right, that times that, so it would be x squared plus 2x. And our next step would be to subtract. So 20 minus 20 falls away, and then we would bring down. So right, let's have a look at what we're doing here. We would now subtract. To subtract, we would change these signs and add. So that would fall away. Plus x minus 2x is minus x. And yes, our next step would be to bring down the rest. Now we'd repeat the performance. So in numbers, we'd say 5 doesn't go into 1, so we put a 0. 5 into 15 goes 3 times, and then we would times the 3 onto that. So we'd say 3 times that is 15. Subtract, we get 1. Same thing happens here. We say x divides into minus x minus once. And then we would say, well, minus 1 times that is minus x. Minus 1 times that is minus 2. Our next step is to change the signs. So it'll become a plus and a plus. That'll fall away. And 12 plus 2 is 14. There's no more to bring down, so that is my remainder. Over here, this would be my remainder because I'd have no more to bring down unless I was planning on using decimal points, in which case I got comma 0, 0, 0, 0, 0. So basically what am I doing when I do long division? I'm breaking it up so that I could write it in a certain format. So for example, what am I saying to you here? Let's get it up a little bit. I'm saying that 5 times, I think it was 403, but let's just make sure, plus 1 would actually equal that answer up there. All right, so what am I saying here? I'm saying x plus 2 times x minus 1 plus 14 will actually equal x squared plus x plus 12. Well, let's see if that is true. It's easy enough to check. So we times this out. We're going to say it's x squared minus x plus 2x minus 2 plus 14, which means I have x squared, and if I add those guys, I'm going to get plus x, and if I add those guys, I'm going to get plus 12, and look at that, there it is. So all the long division algorithm is used for is to change the way we write something. Now, what did our theorem say to us? Our theorem said to us, if we've got a polynomial and we're dividing by something, then the functional value of that something is the remainder. So let's test it out. Let's see if that's true. We know that the remainder of this thing is going to be 14. So let's use our principles here. Well, we know that f of x is equal to x squared plus x plus 12. Let's go up to this one over here. And we see that this is what happens. Now, how did I get this b over a? In actual fact, I sort of thought to myself, ax minus b equals 0. And then I said, well, that means that ax is equal to b, which means x is b over a. So using a similar principle here, I would say x plus 2 equals 0. And so the x value I must use is minus 2 if we're using this theory. So let's see what the functional value of minus 2 is. It'll be minus 2 squared plus minus 2 plus 12. Well, minus 2 squared is going to be 4. This is minus 2 plus 12. If we add that, 4 minus 2 is 2. 2 plus 12 is 14. That is exactly the remainder we got when we used this long division. All right, so you can see that that's one other way of coming up with the remainder, and that's a really efficient way of doing it. And to be honest, that's really all we need to be able to work with our cubic equations and factorize them and organize them. There is a method called synthetic division, which is very, very useful. And I will show it to you just once. I don't think you need to get too worried about it, but just in case, I'll show you at least one time how to do it, which replaces this daddy, mommy, sister, brother algorithm. So right, let's have a look at it, how it works. It's actually relatively easy. So what am I doing? I'm taking x squared plus x plus 12, and I'm dividing it by x plus 2. Now, there are many algorithms for this synthetic division. I like to work with one that almost looks like noughts and crosses. Now, what I do here is I write down the coefficients of the original. So it's going to be 1 plus 12. And over here, just like I did before, I'm going to say if that was equal to naught, the value I would get is minus 2. Now, this value here comes straight down as it stands, so it's just a 1. Then I say that times that, and the answer of that is going to be minus 2. I then add these. That's what's different to the other. So I'm going to get minus 1. I then times that by that, and if I do that, I get plus 2. And I then add these, which gives me plus 14. This last thing here is always the remainder. Now, what does that mean? We started off with an x squared here. We were dividing by an x, so this will be an x minus 1. So I'll be able to write it's x minus 1, remainder 14. As I say, if you need to, this is a really neat way of sorting it out with a long division. But to be honest, I think it's not something you require over much. I'm just mentioning it to you, so should you have a question like that ever, this is an option. And it might be worth trying a few like this and seeing if you can get it to work really nicely. On the X sheet, I'm sure I'll put out an actual reasoned example, step for step, on how to go about synthetic division. Right, let's move on to the next question. Now, this is the typical kind of question. They don't get too carried away with it. It says when f of x is divided by x minus 1, the remainder is 10. Use this to find the value of p if f of x is equal to that. Now, just thinking our theory, f of 1, because you agree with me, what I do is I put that equal to 0 and solve for x, so it would be 1, must equal 10, because we know that whatever we're dividing by, the functional value of that will give me the remainder. Now, what would the f of 1 look like? Well, it means go along to this equation, and wherever there's an x, put a 1. So here you can see your functional notation coming in again, and you're, of course, feeling very comfortable with that, having done that previous session. So it's equal to 2 plus p plus 3, which means we have p plus 5. But they told me that that is equal to 10. So at this stage, I can put 10 in here, and so I know that p is equal to 10 minus 5, and therefore p is equal to 5. Really nice, simple question, and really that's the kind of thing, if you probably got asked anything directly, you would be asked, nothing major. Right, so let's move on now, and let's see what else we could get. Now, this is when we get to the real crux of what this section's about. It says, given that g of x is this story over here, show that x minus 3 is a factor of g of x. Now, when we did the factor theorem, what did we say? We said if we work out the functional value, the remainder would be 0. So what functional value would we be working at? We'd be looking at x minus 3, so we'd be looking at the g of 3. So literally what I'm going to do is I'm going to go along here, wherever there's an x, put my 3. Right, so I'm going to get 2 times 3 cubed minus 3 squared minus 13 times 3 minus 6. And what do we anticipate? We anticipate our answer this being 0. Because if the answer is 0, it means my remainder is 0. And if my remainder is 0, then it means that I have a factor. So this is what I anticipate. Let's see if it's true. Right, so this is equal to 2 times 3 cubed is 27, minus 3 squared, which is 9, minus 39, minus 6. 2 times 27 is 54. And if I add here, I've got minus 9, minus 39, which is going to be minus 48. Minus 6 is minus 54. And yes, exactly what I anticipated happening has happened. I get 0. And therefore, I can say that x minus 3 is a factor. Now, at this stage, we can move to factorizing g of x completely. Now, I just want to keep that there for a few minutes. The actual equation was 2x cubed minus x squared minus 13x minus 6. And what we have just found out is that one of the factors is that. Now, if this is a cubic, we know we are going to end up with 3 factors, assuming they can all be worked out. So we know we're looking for the other 2 brackets. Now, there are a whole lot of cheat ways to do this. One of the ways is using your calculator. If you have the 991 plus, you can get away with using that because it just gives you the answers and you can cheat it back. Or you can use your table method and look for your zeros and pick it up like that, because after all, when you're solving for an equation, the zeros are your answers. But I would like to show you how to do this without the calculator and without cheating, just doing it legally. Now, it's very easy. What we do now is we say, okay, we need to find out what is left if this is a factor. Now, of course, there's nothing wrong with doing long division or synthetic division and coming up with an answer. But I would like to try and show you a method of inspection, which is very, very easy. And it's so time-saving. But I will do it this way, and I will do it the synthetic way, since those are probably the 2 ways that you haven't really had much time to work on. Right, so what I would do is I'd look at this and I'd say, okay, fine. I know that this one times this one must give me this one. All right, so if that's the case, what must go into that yellow splodge? Well, I've got x here. To get 2x cubed, I need 2x squared. All right. Then I know that the minus 3 times this last one must give me minus 6. Right, so if I've got minus 3, what would I have to times by to get minus 6? I'd have to times by plus 2. Right, now at this stage, the only thing I need to do is find this guy. Now, there's a safe way and there's an inspection way. I'm going to show inspection, then I'm going to show you safe, and then I'm going to show you synthetic division. So basically what I would do is I'd look at this and I'd say, if I times there, I get minus 6x squared. Now, I know that these 2 times together must make me come out with the answer minus x squared. So I've got minus 6. I know I've got to lose 5 of them, so I need to have a plus 5. So that must be plus 5x. That means I'm ready to factorize this further and solve it down. So I'm going to finish doing it, and then I'll go back and show you another route. So what I would do now is I'd say it's x minus 3. I would then make this factors like this. I'd go 2x and x, a 2 and a 1. I know that that's a plus, so the signs are the same, both positive, plus, plus. And there you have it fully factorized. Okay, really easy, really simple, and not that stressful. Okay, obviously the more practice you get in this, the better you're going to get. I'll do another one for you now, but let's first do it the other way, the safe way, because the safe way is always good. Let's have a look at that. Well, the safe way goes as follows. We know that x minus 3 is a factor. We can work out this 2x squared very easily, and we can work out this plus 2 very easily, but we don't know what that will be. So what I do is I call it plus kx. Now what I do is I times those and I times those. So I say that's kx squared minus 6x squared, and I know the answer I want is minus x squared. So now I've got a kind of expression, so I can go kx squared equals minus x squared plus 6x squared, which means I have kx squared plus 5x, not plus, equals 5x squared, which means k is equal to 5. So I would go back here now, and I would replace this with 5. And of course, that's the way I got by just looking at the inspection here. And it's quite safe, it's quite reliable, and there's absolutely nothing wrong with going that route. So if it makes you more comfortable and you feel like you can be more dependent on that and not make mistakes, by all means use that little substitution of kx and work out your k clinically and legally. Right, I'm just going to go up a little bit and just throw in the synthetic division for good measure. So you've seen some of that as well. I'm just going to take this little bit off here because I want to have some space to put the synthetic division. Just decided not to rub out. Right, so what we would do is, as I said, I like to use this kind of like noughts and crosses look. I know that we are looking at 2x cubed minus 1x squared minus 13 minus 6. And over here I found 3. Because remember, if x minus 3 is the thing, then if I put in a value, it would have been 3. Now the first step on my synthetic division is to bring down the first number as it stands. So I literally look at this and I push this number down there. I then say this times this, which gives me 6. And I then add them. So minus 1 plus 6 is plus 5. I then multiply here. 3 times plus 5 is plus 15. And again, I add. Minus 13 plus 15 gives me plus 2. I then multiply here, and I get 3 times 2 is 6. I add, I get 0. And the last one here is always the remainder. I knew that was going to happen because I'd shown that it was a factor already. So what happens here? This was an x cubed. So when I put this back, it's going to be 2x squared plus 5x plus 2. And if you look over here, that's exactly what I got there. Again, quite a lot of work when you can do it relatively easy like that. So my encouragement to you is try to master this first way, and I will try and use it a few more times in this lesson so that you can actually see for yourself and work with it and be comfortable with it. Right, let's see what the C question asks. The C question says hence. Now, I'm sure you've heard me many times say to you, hence means do it with what you've got or otherwise get it wrong. But it's not quite as bad as that, okay? I think basically what we're going to do is we're going to take the thing we factorized, and instead of calling it g of x, we're going to put it equal to 0. So let's do that. We have x minus 3 times 2x plus 1 times x plus 2 equals 0. And now all that we would do is we would say, well, that means that x minus 3 is 0, or 2x plus 1 is 0, or x plus 2 is 0. So our x works out to be 3, or here 2x is equal to minus 1, so x is equal to minus a half, and over here x is equal to minus 2. There we have our 3 answers. Now what they're preparing you for here now is when we start curve sketching, you're going to have to work out your x-intercepts, which would involve this kind of factorization. Obviously, they're not going to be so kind as to say, show that something's a factor. Well, they might, but it's unlikely. So what I need to do now is perhaps to show you how we make our decision on how something is a factor. Let's look at the next question. Given this, determine all values of x so that f of x equals 0. So we're jumping straight into the frying pan here. So what we're going to do is we look at this last number here. If something is a factor of that last number, it has the potential to be a factor. So in other words, I could try 1, I could try 2, I could try 3, and I could try 6, likewise, minus 1, minus 2, minus 3, minus 6. It's no good trying 5. I can already see that 5 will not work because of the 6 at the end there. So I have to be careful to choose factors of that last number there. So what I would do now is I would start by looking at one of these. What I normally do is I look at it and I say, we've got plus, plus, minus, minus. Chances are it's a positive because they're an even amount of positive and negative numbers. So let's start this side. If I look at the 1, I can see immediately I'm not going to have success because it's 2 plus 1. It's going to be much smaller than minus 7 plus minus 6. So that's not going to work. So let's start with the f of 2. If I start with the f of 2, I've got 2 times 2 cubed plus 2 squared minus 7 times 2 minus 6. 2 cubed is 8. 8 2s are 16. 2 squared is 4. Here I have minus 14 minus 6. And if you work that out, you're going to get 0. Therefore, x minus 2 is a factor. Now, that doesn't mean to say that you would have to have got that as a factor. You could have got any of the 3 as your factor. But it doesn't matter which one. As long as you show me that if you put it in, you get 0, then I know it's a factor. So don't worry if you were sort of working ahead of me and you've got a different factor. You'll see your factor will come up in the next step. So right, what am I going to do? I'm going to go x minus 2, and I'm now going to go looking for the rest of that expression. Okay, so right, we know, let's start here, that this one times this one must equal that. So what must go into the yellow splodge? Well, it must be 2x squared. Right, let's go to the green splodge. If we have the green, oh, the green is not a good idea against green, so let's just make these black. So 2. Okay, and I'm looking for that over there. And I want the green splodge to be minus 6. So I need that over there. So I've got that there. Well, if I look at it to get a minus 6, I would have to have a plus 3 over there. So that'll be a plus 3. Now it's up to you whether you want to use that method where you just do inspection, or whether you would prefer to work with that k. I'm going to just do it by inspection, and then you can decide for yourself what suits you better. So let's look at it. I would times like this, and I get minus 4x squared. Now I know whatever I times there must complete it and give me plus x squared. Well, if I look at it, I need to get a 5 there in order to get that right. So I need a 5x over there. And you can see if I times there, I would get 5x squared. And if I added those, I would get plus x squared. So yes, that works. Otherwise, we can use the k, or at very worst, we can use our synthetic division. Right, so having done that, we can now carry on the question. So we can look at this now and we can say, well, that'll be x minus 2. And over here, I can factorize that and get 2x and x. Okay, it must be a 3 and a 1, a plus and a plus. So there's my answer. So you might have got x equals minus 1 as one of your factors to start. I'm going to show you that now just to show you it won't make any difference. So I know that x minus 2 equals 0, or 2x plus 3 equals 0, or x plus 1 equals 0. So here we have x equals 2. Over here we have 2x equals minus 3. So x is minus 3 over 2. And over here, x is equal to minus 1. So there's our three answers, relatively straightforward. If you had got the x plus 1 as your factor, let's find by inspection the rest of this. Let's just get the equation up again. Well, we know we wanted 2x cubed, so that would be a 2x squared. We want to get a minus 6, so that would have to be a minus 6. That gives me 2x squared. And I want to get 1x squared, so I need to subtract an x. So that means I would have got x plus 1, and I would have factorized this thing. If I do that, it's 2x and x. We want factors of this, which are going to be 3 and 2. We want to get a minus 4 and a plus 3. And as you can look at it there, it's identical. So it really doesn't matter which is the first factor you find. You will always get the same answer if you're careful and precise. All right, so now let's see what the last part of the question said. Again, that magic word, hence or otherwise. Now, if you look at this, what relationship does this bear to this first one? Well, if we look over here, let's tidy this up a little bit because we need some clarity. But if we look at this, and let's take the yellow highlighter, this x, and this x in this one over here have been replaced with x minus 2. So if I let x minus 2 equal k, I would have 2k cubed plus k squared minus 7k minus 6 equals 0. And if you look back to what you started with, that is exactly the same equation. So what am I saying to you? I'm saying, well, in this case, the answers would be k equals 2, k equals minus 3 over 2, and k equals minus 1. But our k is this bracket. So at this stage, I can go along and I can say, let's make it black, that x minus 2 will equal 2, which means x is 4. X minus 2 is equal to minus 3 over 2. Now, if we bring that over, it's going to be x equals minus 3 over 2 plus 2, which will just be a half. Or here, we've got x minus 2 equals minus 1, which means x is equal to 1. So there we have our three values for this particular equation. But the hence or otherwise is our giveaway. Why are they using that word? Well, they're using that word because that's how you're going to do it. Otherwise, why would they bother to write hence or otherwise? It's a hint that you need to go back and use it. All right, let's move on now. We are going to now talk about sketching a cubic function. Now, sketching a cubic function involves certain steps. And basically, I'm going to outline them for you because it's quite important to understand. The first thing I would always do when I'm thinking of sketching a cubic function is I would discuss the shape. Now, I'm sure you're used to it from your other graphs. We always looked at the shape. So let's assume we've got y equals ax cubed plus bx squared plus cx plus d. That being the general form, if you like, of a cubic function. Do you agree with me? The shape was always determined, especially on a parabola, by the value of a. So again, the shape is going to be determined by a. Now, if a is greater than 0, I will show you a more mathematical way of doing this. But at the moment, I just want to give you some nice little pegs to hang your thinking on. If A is positive, we get what we call a slinky graph. And of course, slinky is slang for what's happening here. It's a much better, more mathematical term for that, but it's a nice way to remember it. And the graph will either look like this or it'll look like this, depending on how many turning points or stationary points we come across. Now, I'm going to explain that to you in a little while, but you can see it's got that shape. It goes with my hand along the way. If A is less than 0, we have a kinky graph. Kinky because you're going against your hand. Likewise over there, again depending how many stationary points we've got. So we'll either take this shape or this shape, and in this case we'll take this shape or this shape. So the first thing I would always do is decide my shape. This just enables me to get a better idea of how my curve is going to look and to build my points as I go, and you'll see what I mean when I actually start sketching. Right, so going over to the next thing I would do is I would find what I call the stationary points. Now that's a new concept to you. You've heard of turning points, but I'm calling these stationary points, and you will see often, very often in fact, when you are looking in exam papers, they use the word turning point rather than stationary point. Stationary point for me is a better name for it because what I'm saying to you is the gradient of the curve becomes 0. So if we're looking at the curve and we're looking as it going up, it's got a positive gradient, then it goes into a negative gradient. And as it does that, it must surely go through 0 to change from positive to negative. So looking over here, do you see that if I started over here and I said, right, this is a positive gradient, and then it goes to negative gradient, then it goes to positive gradient. So obviously over here, it had to go through 0 to swap into that. And over here, it had to equal 0. Now here, what's happening is it's got a positive gradient. And yes, at that, what we call a point of inflection, the gradient is also 0, but it doesn't swap. It keeps going up positively. We'll spend some time on that in a little while. Don't worry about that too much at the moment. Likewise, over here, we've started negatively. We've then gone positively and then negatively. So what we're going to do is this is where our gradient is 0 again, and this is where our gradient is 0. And likewise here, this starts negatively and carries on going negatively. But at some point, we reach a point of inflection, and I will talk about that, as I say, a little later, where it will change that direction. So stationary points, they could also refer to as turning points. I'm not wild about it, but I have left it where I found it in questions because you're probably going to encounter it. Right, now let's talk about stationary points. They are found, because they are where the gradient is 0, when the derivative of the function equals 0. Now what we'll do is we'd find the derivative, we'd put it equal to 0, and we then solve for x. To find the y, we substitute x values back in the original. It's no good going back to the derivative, because if you put it in there, it's just going to give you 0 again. So you always go back to the original, or the f of x equation, because that's where you're going to find your y's. Right, some teachers don't teach you to put stationary points next. They teach you to do x-intercepts next. But quite honestly, I believe you're better off doing the stationary points, because often they help you out with your x-intercepts and make your arithmetic that much easier. So my advice to you is, if possible, do them first. It's not the end of the world if you don't, but it just does make it easier. So let's move now to the next thing you'd find, which is the x-intercepts. Now, those we've been doing with graphs for as long as you can remember, and to do that, we let y equal 0. Now, you can see if you're doing that, you're going to get a cubic equation to factorize. And of course, you know how that works. It's quite a lot of work, as you've just seen when we were working on that section earlier. The fourth thing we would go for is, of course, our y-intercept. And to do that, we let our x equal 0. And of course, that's easy, because then our y will equal d. Really easy and simple, straightforward. The last thing we do is we look at our point of inflection. Now, basically what a point of inflection is a point where the concavity changes. It'll either change from concave up to concave down, or it'll just keep on, as you saw, like kind of flicking upwards again. So basically how we do that is we find the second derivative and we put it equal to 0. We solve for our x and we substitute back for the y. Now this will all make sense when we start working on one. But just talking about concavity, I want to talk about what I mean by that. If we're looking at a graph like that, this would be concave down and this would be concave up. So what I'm saying to you is at a certain point here, let's call it about here, the second derivative, so let me just think of how I'm going to write that for you, would equal 0, which means it's changed from concave down to going concave up. And what it does is it affects the way the tangent to the curve will lie. It will lie above the curve over here, and as we go to this side, it lies at the bottom of the curve. But that's not anything to worry about too much. Basically what we're doing is we're changing it from down to up. So to find a point of inflection, we find the second derivative equal to 0. And what we do now is we substitute x value in original for y. So by the original, I'm meaning the f of x equation. All right, so that is like a breakdown of the 5 things we need to do to successfully draw one of these curves. They love asking this because it tests quite a lot of understanding. And I'm going to show you some really fascinating things, and you're going to say, oh, is that where they got it from? And you're going to get quite excited about it as we go through these things. Lots of the things you do in science, lots of the things you've done in maths already in grade 10 and 11, all going to come back to say hello to you yet again. So let's look at a question. Sketching a cubic function. They give me f of x is equal to 2x cubed plus x squared minus 20x minus 28. Show that x plus 2 is a factor. So they're being very kind, because you can see that if you didn't have any hint, 28 would be quite a lot of hard work. You'd have to look at all the possible factors of 28, so you would try 1, and then hopefully you get to 2 next. If you didn't try negative 1, again, it's an even amount of positive and negative signs, so chances are it's a plus thing. But it wasn't in this case. They said a minus 1. So they say show that this is a factor of it and hence determine all the factors of f of x. So this time they're throwing you out of order. They're actually getting you to work out the third thing before you actually get to sketching. And that's fine. It's not a problem. We're just going to work according to what they've got planned for us. So let's have a look. How do we show that? We're going to work out the functional value of. Now remember what we do. We take this and we say if that was equal to 0, then x would equal minus 2. This we do in our heads. Okay, so we're going to put in a minus 2 there. I'm going to go along wherever there's an x, we're going to plonk in our minus 2. And we know that in order for it to be a factor, that must work out to be 0. So put in minus 2, minus 2, minus 2. Right, so order of operations tells me I leave the 2 there and I first raise to the power. So minus 2 cubed is minus 8. Minus 2 squared is plus 4. A minus times a minus is a plus 40 minus 28. Right, so this is going to be minus 16 plus, and we might as well add these guys, they're 44 minus 28. And once I've done that, let's just bring this down a bit, I can see that that will give me 0. Therefore, x plus 2 is a factor. Now it says, hence, find all the factors. So now we have no choice but to go and actually factorize that using that method I was just showing you a little while ago. So let's have a look. We would go over here and we'd say x plus 2. And we'd say we want to find out what's left. So we know we want to get a 2x cubed. So we need a 2x squared over here to get that right. Then we need a minus 28. We've got a plus 2 there, so we need a minus 14 over there. And then last but not least, we need to times those, which will give me 4x squared. And now I know that whatever I times there must make sure I get a plus x squared. So I've got plus 4x squared. I need to have a minus 3x over there. Right, good news is hopefully that now will factorize for me. As I say, you can always cheat with your calculator, but I would like to think that you're learning something here and it's useful. So we're going to get x plus 2. And we go over here and we're going to go 2x, x. We've got factors of 14, which will be 7 and 2. So let's put 2 there and 7 there. Let's check it. We're going to get a 4 and a 7. So that'll be a minus and that'll be a plus. So we have the factors of that thing. Now, it says determine the coordinates of the turning point. Remember, I warned you about that. They might have rather used the word stationary points. As I say, I left it when I found it. I didn't worry about it too much. So what we know is that f of x is equal to 2x cubed plus x squared minus 20x minus 28. For a stationary point or a turning point, what do we do? So I would write an examiner a little note. For a stationary point, f dashed x equals 0. You're asking me, is this necessary? No, it's not, but you know what? It just helps your examiner. If they see that you are very nicely setting this out, and you do make a careless error, they can still give you method marks if you've clearly indicated to them what you're doing. So it's always a good thing to write more than you need to. So right, over here, we find the derivative. So f dashed of x will be, now remember how it worked? We said 3 times 2 is 6, x squared. That 2 goes in front, so it's plus 2x. And that's a 1, so it's going to be minus 20x to the naught. We don't worry writing it. Now we know that that must equal 0. Now if we look at this, we can see we can make our lives just a little bit easier, because we can say to ourselves, let's divide through by 2. If we do that, we've got 3x squared plus x minus 10, which is always easier to work with. And so here we go with our factorizing, 3x and x. We've got 2 and 5. We want to get a plus 1, so we need that. And so we get the answers x equals 5 over 3, or x equals minus 2. Right, so next question says draw a neat sketch. But hang on, we're not finished. I just nearly forgot the most important part. They want the coordinates of this turning point. Coordinates mean we are looking for our x and our y value. We've got our x value, we need to go back and find our y value. So let's go to this and let's have a look. So what I'm going to do is, remember I said I go back to the original and I solve it out there. Just by the way, here the calculator is a useful tool to have. I'm going to be good and not use a calculator, but in actual fact, if you went 5 divided by 3 equals, it'll go into your answer. And then when you key it in, you just use the answer to get this fraction to work out for you really nicely. But since I'm trying to set a good example, let's work without the calculator. Of course, it's better to work with a calculator than get it wrong, so just remember that. So y will equal 2 times 5/3 cubed plus 5/3 squared minus 20 times 5/3 minus 28. Right, so doing that, it's 2 times, and 125 is 5 cubed, and 3 cubed is 27. Plus, the squared is going to be 25 over 9, minus, this is 100 over 3, minus 28. All right, so doing that now, we go over here, and we're going to tidy it up a bit more. I actually should have left myself some more space, but we'll make a plan in a little while. So if I do 2 times that, I'm going to get to 250 over 27 plus 25 over 9 minus 100 over 3 minus 28. So now you can see why I'm saying it's actually a nice idea to just use the calculator. A colleague of mine always says that if there's a 27 at the bottom, you know you're probably right. And I think it's quite a good rule of thumb. It seems to be something that they quite like. I haven't seen many other funny numbers at the bottom. It's usually a 27 or something along those lines. So just remember that it's worthwhile thinking about. So it becomes 250. 9 goes into 27 3 times. 3 times 25 is 75. 3 goes into there 9, so it's minus 900. And here I've got 28 over 1. So that's pretty hideous. So what I'm going to do now is I'm going to say 28 times 27. So we put on the 0, we go 6, carry the 1, and that's going to give me 4 plus 1 is 5. And then I'm going to do the 7, so it's going to be 7 8s are 56. Carry the 5. I hope I'm right there. Yes, I think I am. 7, 3, yeah, that's right. So that's 14 plus 5, which gives me 19, which, assuming I'm not making any mistakes arithmetically, come out to be, let me just check I haven't added right, 756. Okay, and now it would just be a matter of working that out, which is pretty hideous. Yeah, I definitely need some more space. So let's go over here. I'm sorry, I'm jotting all over the place here. So it's 250 plus 75, which is going to be 325. And from that, I must subtract 900 minus 756, which is minus 1656 over 27, which is equal to, and I definitely think at this stage you're saying, please bring me a calculator, life will be easy. So maybe we should stop for a few seconds and just look at the calculator and show you how much easier your life would have been. It also serves as a good check for my arithmetic. So that's 1, that's going to be 3, and that's going to be 13. So it's going to be a delightful number, 1331 over 27. Now, if my colleague is right that if it's over 27, all is good, we'll see when we use the calculator if that is so. Right, let's pull up the calculator. I've got one here. Let's put it down and let's actually use it to work this out. Remember what I said to you, the first thing we do is we take 5 divided by 3 and we press equals. That means this thing is in the answer. Now all I've got to do is input it as it stands. So it tells me 2 times the answer cubed. Now the little button for cubed is this one here. Depends what calculator you've got, of course you would have different buttons. Then I go plus the answer squared. Unfortunately, there is a button for that. Minus 20 times the answer, minus 28 equals. And I come out with the answer of, let me write it down over here, minus 49,3 basically. Let's see if my answer was right. 1331 divided by 27 equals 49.3. So yes, it was right. But you can see it was quite a mission compared to just using our calculator. Right, so going over here now, we can clean this up a little bit because it's really quite difficult to see what's going on here with this, all this working here. We've got our answer, and we can write it as a coordinate. Okay, right. So we have a coordinate, 5/3, 1331 over 27. Or if you like, you could write 5/3 with negative 49.3. Now, obviously, negative 49.3 means a little bit more to you than, say, that horrible fraction I had there just now. But obviously, the fraction is always better, sadly. Right, let's go and work out the other y value. And let's be lazy. Let's use the calculator because it just saves some time. So going over here, we're going to take the value of minus 2. So remember how I did it? I put the minus 2 in, and I pressed equals, which means it's now in my answer. So I would go 2 times the answer cubed plus, sorry, I nearly made a mistake there. It's not 2, it's just the answer squared minus 20 times the answer minus 28 equals. And I get the answer 0. So y is equal to 0. So I have a coordinate minus 2, 0. Right, now what we're going to do is we're going to finish up this question, and you'll see that the very next thing they ask you to do is to sketch a neat sketch of this. Now, remember what I said to you right in the beginning. I said when we look at it, the first thing I would like you to do is to look at the shape. In fact, let's just take it over here and just put this equation over here. So f of x is equal to 2x cubed plus x squared minus 20x minus 28. And what did I tell you? I said to you, we look at the a value. It's 2. So I know it's going to be a slinky. We know it's this shaped slinky because I've got 2 stationary points. Now looking over here, this is the first of the stationary points. Now how do I get to that? Well, what I do is I look at these x values. A minus 2 is smaller than a 5/3. So I know this must be minus 2, 0. So it's going to be 5/3 with 1331 over 27. Okay, so what we have there is what the curve sort of is going to look like. Obviously, there's a whole lot of other stuff we have to do. They asked me now for the x and y intercepts, as well as the turning points. The turning points have been done. There they are, because that was when we put the stationary point equal to 0 and we solved. Now, we're going to go for the actual turning points. Now, right in the beginning, they had asked me to show that x plus 2 is a factor and hence factorized. So in actual fact, we've already done that. Now I want you to notice something, and this is quite a useful thing to notice. That x plus 2 repeats twice. The moment that happens, that is a stationary point. So if x plus 2 is repeating twice, that is a stationary point, and it will be on the axis, and it will serve two purposes. So really, very, very easy to work with once we've established that. We know that our stationary point is there. Right, so let's go down to the actual graph. So we know that that's repeating. So we knew that it does help if one changes to a pen that works instead of a highlighter. So we would have had x plus 2, and this last one here would have been 2x minus 7. So our x-intercepts were minus 2, which is the same for that one, and x is equal to 7 over 2. So we know that this is the coordinate minus 2, 0, which we know, and we know the coordinate 7 over 2, 0. So the x-intercepts, no problem at all. Y-intercept, also no problem. For y-intercept, we let x equal 0, and if we do that, our y is equal to minus 28. So we have a coordinate 0, negative 28. Now, this particular question never asked me about a point of inflection, but we could have a look at it just for completeness, just to show you. But first of all, let's draw with what we've got, and then I'll talk to you about the point of inflection. Let's get ourselves an axis. So we want a reasonable axis. Obviously, there's no way we can accurately draw this to scale. Just look at these horrid numbers, and you know that there's not going to happen. So what do we know? We know that at minus 2, 0, we have a stationary point. Over here at 5/3, see, that's not to scale, but that's not a problem. So it's 5/3 with negative 1331 over 27, which is negative 49 comma something. And over here, we know that this is going to be minus 28. You can see the scale is definitely not right, but we're not worrying about it because in drawing it, we're sketching it. We just got to show all the important things. The other x-intercept is at 3.5, so that's 3, there's 4. 3.5 is over here, so we go 7 over 2. Now, what do we know? Now, this is where this little sketchy thing is quite useful. We know this is what we call a relative maximum. Relative because it is a maximum, but there are points that are higher than that. Likewise, this is what we call a relative minimum. And again, relative because if you carry on down here, there'll be points lower than that. So I know that this has this kind of shape, and I know that this one has this kind of shape. So now what I do is I'd go along to the graph and I draw it. Oh, talk about missing the point. Let's go back here and plonk it in neatly. And there's our point that I had put in there. So really, the examiner would be quite happy with this because they could see. I'd shown them where the x-intercepts were. I'd shown them where the y-intercepts. I'd shown them where those are. And the shape was correct. It might not be perfect, but it was correct. So he would be quite, or she would be quite happy with that. There would be no problem. Right, let's talk about points of inflection, although that was not part of this question. Let's stop for a few seconds. Let's erase this. And let's talk about how we found the point of inflection. You remember in the notes, I said to you what we do is we take the derivative. Let's just get a color pen that works. And we have f dashed x, which would have been 6x squared plus 2x minus 20. And we'd, of course, worked that out earlier on. For a point of inflection, we would find the second derivative. Now, doing that, we're going to say 12x plus 2. And we're going to put that equal to 0 for a point of inflection. So 12x plus 2. So minus 2 is equal to 12x. And so x is equal to minus 1/6. Now, knowing that, I could go to my drawing. And I would know that at minus 1/6, about over here somewhere, let's take another color. Over there. The concavity changes from concave down to concave up. Now, if they'd asked me that, they would have also expected me to put this back and find the y value that goes with it. So it would have been a lot of work, but it wouldn't have been a problem to do. So that's an example of how we sketch a curve. Sometimes they're not as kind as this. Sometimes they don't break it down into little bits. They just say sketch and they give you the equation. But if you use my 5-point plan, you actually have quite a reliable way of sketching it. So let's see. This is another one. I don't think we're going to do this one. I think I'll put it on your X sheet so you can try it yourself. But we'll just quickly have a look at what the gist of the questions are so that you can actually see if you're okay with it. But you'll see it follows much the same format as the previous example. Gives you an expression, It asks you to show that that's a factor. It asks you to factorize. And of course, why are you factorizing? You're factorizing to find the x-intercepts. It asks you to find the derivative and hence the coordinates of the local max and min. Remember what we talked about? This would be considered the local max, and this would be considered the local min. So if they want that, they're actually asking for the turning points or the stationary points of this graph, and they're just asking you to be more specific about what type of thing it is. All right, let's see what else they ask. They then ask you to find the coordinates of the points of inflection, which I've shown you how to do. They then ask you to sketch the graph and answers provided. And then last but not least, they ask you to find the equation of the tangent to the curve. Now that one I'm going to do with you. The others you can do on your X sheet. I'll put them there as an example. So let's go to the next page because I think I had it over here. Yes, I did. There's your question. It's f of x equals, and I'm just going to write it down here so I've got it at hand, x cubed minus 3x squared minus x plus 3. Right, now they want me to find the equation of the tangent. So again, I'm just going to write it here so I can keep moving down the screen. With not doing the whole question, we are in a bit of a disadvantage. Here you go. Determine the equation of the tangent to the curve at f where x is 2. Now remember I said to you that these questions, they would either tell you where the point of contact was, and then they would ask you to find the tangent. This is just such a case. They're telling you at x equals 2. Now, if it's x equals 2, you're going to go and put that 2 in and find the y that goes with that. So let's have a look here. We're going to say, what is the f of 2? Well, it's 2 cubed, 3 times 2 squared, minus 2 plus 3. You probably would have found you'd find this point somewhere else in the question. So it's 8 minus 12 minus 2 plus 3, which is going to give me 11 minus 14. 11 minus 14 is minus 3. So we have a coordinate 2 minus 3. Okay, so once we're here, we have the point of contact. The next thing to do is to find the actual gradient. Gradient is derivative. Just remember that very clearly in your mind. So it's 3x squared minus 6x minus 1. And we want to know what is the gradient at 2. So it's 3 times 2 squared minus 6 times 2 minus 1. Right, moving that down a bit, we can see we're going to get 4 times 3 is 12, minus 12 minus 1, which is really nice to get minus 1, which is the gradient of my tangent. So using my method, we can go y minus y1 equals gradient x minus x1, which means I have y plus 3 equals minus x plus 2, which means y is equal to minus x minus 1. Okay, and if you wanted to use the other way of getting your tangent, feel free. It's not a problem. It's whatever you're most comfortable with. So the only thing different with this question to the previous question was a little bit on the tangent. And I said you will find it in your graph interpretation quite often. Right, here's another graph interpretation. And once again, I think we'll just discuss the approach, and it will be on your X sheet, so you can try it for yourself with the answers and see how you do. If there's anything strange or different, we'll talk about it. Let's have a look. Below are the graphs of f of x equals x squared plus 4x plus 3 and g of x a cubic function. The two functions have roots at a and b. Roots. Now you hear the word roots, and I have mentioned this before, but I'm going to say it again. Roots is another name of saying your x-intercepts. So when I say it has x-intercepts at a and b, it's literally I want you to go and solve for when y is 0 at that graph. And it has another root at a half. Okay. The length of DE is 6 units, so that's quite interesting. You'll see why now. Well, I want you to find A and B. That won't be problematic because you do have the equation of the parabola, and you can do it very easily. So once you had this value, and of course you know that this one is a half. They told you the other one is that. Okay, then they say, after having asked you to find A and B, which is relatively easy, give the coordinates of E. Now, E is where that y-intercept's happening. Now, of course, we know that this is 3 on the parabola, because if you let x equal 0 here, your y will be 3. They've told me this distance is 6, so E's coordinate must be 0 minus 3. So really relatively easy if you just keep your wits about you and you're careful. The third question says find the equation of g of x. And now this is where I want to stop for a little bit. So maybe we just need to actually get those x roots because we're going to need them to explain this. In fact, before we go there, let's go to another page. and let's just talk about it. Now, you've done finding equations of parabolas and all other graphs you've drawn. This is not really very different in any significant way. Supposing I've got a graph like this and I tell you that's minus 2, I tell you that's 1, and I tell you that's plus 2, and I tell you this is 12. Now, if this had been a parabola, so in other words, say it had looked like this rather, 1, 2, 2. How would you have gone about it? Well, you would have looked at it and you would have said, look, I'm given my x-intercepts. If I'm given my x-intercepts, I can use the equation y equals a, bracket x minus x1, x minus x2, and then work with it. So let's just run that through so you can see it for yourself. So this is what it would have looked like, the format of the equation. We have done this before in one of our revision sessions. So our y would equal a. This would become x minus 1, x minus 2. And we'd see that the only thing we are missing is our a value. So we need to have another point, and we do have another point, 0, 2. So we're going to take 0, 2 and sub it in. So 2 is equal to, let's bring it up, a, and this is going to be 0 minus 1, 0 minus 2, because remember that's an x, although it sure looks like a 2. Now this is equal to 2, and this here is a, and it's minus 1 times minus 2, which is 2, which means a is equal to 1. So we have the equation y equals 1 lot of x minus 1 times x minus 2, and all we'd have to do then is multiply it out. So it would be 1 times x squared minus 3x plus 2, which would have given me x squared minus 3x plus 2. Still staying with a parabola, because I think if you understand the parabola, this is not a big jump. If I had drawn the following, and I'd given you that, you would have said to me, well, hang on a moment, I've got the turning point, 2, 0. And the turning point is y equals a, x minus p all squared plus q. We would have then gone over here and said, this is your p and this is your q. So you would have got y equals a, x minus 2 all squared plus 0. In other words, y is equal to a, x minus 2 squared. Now, of course, what does that mean? It translates to the fact that if the turning point is on the x-axis, it actually is repeated x value, if you like. Now, remember, I mentioned that right at the beginning when we were sketching the cubic. I said if that ever happens, that your stationary point is also an x-intercept, and it means it's tangential to the x-axis. Well, this is exactly the same kind of thinking. So yes, we could have done that. So let's now move to the cubic, because we're not, the purpose of this lesson is not to look at a parabola as such. So let's move ourselves down, and let's see how this is going to be different. It's always good to hang your hat on old work so you understand where this is coming from, and you'll see it's just a little leap, and it's very important when you learn maths that you realize how everything connects together, because it's a beautiful subject. You know, they're talking all the time about soccer being the beautiful game. Well, maths is the beautiful subject. So we have a, there's a factor, and there's a factor. And now we're ready to actually go about it the same way. Of course, because it's a cubic, we've got 3 brackets instead of 2 brackets. That's all that's different. And all we're going to do is we're going to go over here and we're going to say x minus x1, x minus x2, and x minus x3. Now we have y equals a, x minus minus 2, x minus 1, which is quite nice, and x minus 2. Okay, just like with a parabola, we still have our a missing, so we need one other point for that. And do we have another point? Most definitely we do. We know this coordinate. This coordinate is 0, 12. So let's go along and substitute in 0, 12. So wherever there is an x, I'm going to put a 0. And where there's a y, we're going to put a 12. So 12 is equal to a, 0 plus 2, 0 minus 1, and 0 minus 2. So we have 12 equals, and now we're going to tidy up. So it's a, this is going to be 2, times minus 1, times minus 2. So 12 is equal to. Now if we multiply these numbers together, 2 times minus 1 is minus 2. Minus 2 times minus 2 is plus 4a. And so a is equal to 3. So now we have y equals 3 lots of x plus 2. And you might notice I'm taking a little bit of poetic license here and shuffling them. because you'll see the arithmetic becomes easier if I do that. By doing that, I've now got those together, which are just the difference of squares. So if I times the 3 by that, I would get 3x minus 3. And timesing those, I would get x squared minus 4, which makes this whole finished product much easier. That times that is 3x cubed. That times that is minus 12x. That times that is minus 3x squared. And that times that is plus 12. All we can do to improve on the issue here is perhaps to just write it in descending order. So let's just do that so it's really complete. But you can see not such a problem question. 3x cubed minus 3x squared minus 12x plus 12. All right, so that's how we do this, and it's relatively easy. All I want to say in the way of finishing this off is to say if we have a situation like this and that's a 1 and say that's a minus 2, all we would do and say that was 24, I don't know, whatever. Then all we would do is we'd say this one is going to be a x plus 2. Then because this one is a tangent here, we repeat that bracket twice. And then you can see we've got our 3 brackets and we would proceed normally about this. Right, let's see what the rest of the question asks, and we'll deal with things we haven't dealt with before. Let's go to it here. There's the graph again. You know we've calculated a whole lot of points already, so let's just highlight them. We know this, we know this, we know this, we know this, and of course we know the curve's equation. Now the question, the very next question says, find the coordinates of k where the two functions intersect. So there it is. We already know these two, so we only have to find this third one. And all that would involve is us working with a simultaneous equation. So what we do is we'd substitute the one equation into the other, like we've done many times before working on graphs. We'd factorize the thing, and it would be easy to factorize because we already know 2 of the answers. And we'd find the third one. So that's not a problem question, and as I said, it will be in your X sheet, and you can then have a look at it and see for yourself. Let's see what the next question says. It says, does f, the turning point of g of x, lie on the axis of symmetry of f of x? All right, now that's quite interesting because you've obviously worked that out somewhere. But before we go, I'm not actually going to discuss this too much. I just want to show you something that's really cool and worth knowing. As you know, this is the general form of a parabola. Now, if I find the derivative of that, I'm going to get 2ax plus b. Now, for a stationary point, or if you like, a turning point, we put the derivative equal to 0. So we get 2ax plus b, which means minus b is equal to 2ax, which means x is equal to minus b over 2a. Now, I can almost hear you all going, whoa, we didn't know that. Well, of course, you would realize that this ties straight into your grade 11 work when you were taught that if you have to find the axis of symmetry, you would just use the formula x equals minus b over 2a. So you have calculus that enables you to find that axis of symmetry, or you can use the formula for a parabola, that is, not for a cubic, to find that axis of symmetry. So I'm not going to get into that. You can also manage that easily enough. Let's see what the last question is, and that one I am going to do. There are 2 x values where the two functions are increasing at the same rate. Find these values correct to 2 decimal places. Now, as soon as you hear the word rate, and now next lesson we will spend a lot more on that, rate implies derivative. So what we would be doing is we'd be taking the derivative of f and putting it equal to the derivative of g. And then we would solve for x, and that would give me 2 values. They've told me that there are 2 values where this happens. So what we'd literally do is we go back to our graphs, if I can get back there. We would have this equation now. We'd worked it out. We'd have this equation. We would put them equal to each other and solve for x. So really a relatively exciting question, something different. And they've told you there are 2 answers, so you know you're right when you get your 2 answers. Right, so at this stage, I think it's a good time to stop. We'll pick up from here in the next lesson. Remember, the next lesson, we're going to type some loose ends around sketching and graph interpretations. And then we're going to move across to maximum, minimum problems and rates of change. Both very exciting, powerful bits of calculus. Now, I look forward to seeing you next time. Have a good day.